So Nate, feel free to kick off your deal or no deal talk whenever you like.
Fantastic. All right. So I'd like to start this talk with a really high-level philosophical question of humankind. Let me actually click to my slides. There we go. Okay. So you're going to flip a coin, and depending on how the coin lands, you'll either get $1 or $1 million. And right before you flip the coin, I say, wait, don't do it, stop, because if you don't flip it, I'm going to give you $500,000. Do you decide to flip the coin, or do you take my deal? What if I offered you 750,000 or 250,000? What's that, right sweet spot amount that I can offer you to walk away from flipping the coin entirely? So this whole scenario is really just applied risk versus reward, a really simple scenario. But risk versus reward is what makes us us. Each of us have our own internal balance of risk versus reward, and none of them are the same as any other. And this very fundamental principle of humankind is best exemplified through the TV game show Deal or No Deal. So my name is Nate Jones. I'm a data scientist here at ShopRunner. My pronouns are he, him, his. And today I'm going to be spending half an hour talking about how we can understand and eventually play Deal or No Deal better than a human. So a little backstory on Deal or No Deal. It's not a very highly reviewed game show unless you're on Facebook. Facebook really loves Deal or No Deal for some reason. My favorite review is from the Boston Globe, who says, it's only a few shades more adult than, say, playing with blocks, which if you've seen Deal or No Deal, you'll agree, it's not a very complicated game show. But as I watch this seemingly simple game show, I keep thinking, can we use machine learning in some way to master it or at least understand Deal or No Deal a little bit better? And so to me, Deal or No Deal is really essential to growing up. I don't know who I would be without Deal or No Deal. But talking to a lot of people at ShopRunner, I realized so many people have not seen Deal or No Deal, which is just absolutely insane to me. So the first part of this talk will be statistics and machine learning free. Let's just talk about how the game Deal or No Deal actually works. So the game starts with 26 models. Each of them hold a case, and each of these cases has an assigned monetary amount to them. So you can see that these amounts the cases have, they range from a penny all the way to $1 million. As the game starts with the very charming Howie Mandel telling the player to pick a case, the player might pick, case 7, and then the rounds progress with the player opening cases one by one. So they might open the penny case, and this is considered the best move in the game, because the penny case means that the player's case that they're holding, in this case, case number 7, does not have a penny, which means they're going to walk away with some amount higher than a penny. So at least they're going to get $1, which is good news. They can do an okay move like the $100,000, which is fine because the $1 million could still be in the player's case. And then the absolute worst game, or the worst move in the game, is opening the $1 million case, because this shows that the player's case is not holding $1 million, and the audience is really disappointed, and the player looks like they're about to cry. It's really wonderful. And this is kind of the worst move in the game. So at the end of each round of this very seemingly simple premise, there's this little twist with the banker. And the banker is only represented by the silhouette figure. You never hear the banker actually speak. It's always watching the player. And the banker will present the player with an offer to buy out their case. So if we think about this coin flip example from the beginning, the banker says, I will pay you this much money to stop playing the game right now and just give me the case. And then the player can say one of two things. They can either say deal, or they can say no deal. And if they say no deal, the banker goes away, and then they continue opening cases for the next round. And that just happens for 8 rounds, which is a lot, until you get to the final round, round 9. And then the game is finally about to end. There are 2 cases left, the one that the player has and the one that's left on the stage. And there are 2 scenarios that this can go, and I'm sure you can guess what the 2 scenarios are based on the title of the game show. Remember, simpler than playing with blocks. So the banker can make an offer, let's say 71,000. The player can say deal. They trade in their case, and then they accept the banker's offer, and they walk away a thousandaire. Or they can say, you guessed it, no deal. The banker's offer is officially rescinded, and then they open their case, and they can have a really good case that's higher than the banker's offer, like 500,000, and they're really excited. Or they can have a case that's really lower, like $1, And that's a huge crushing blow. And again, it's always really funny. And that's it. Yeah, so Deal or No Deal is a very incredibly simple game to play. But I'd like to challenge that notion that I just said, that it's a simple game, and we can start analyzing it and realize there might be a little bit more complexities to the game than what meets the eye. So in this section, I'm going to pose a bunch of questions, and I'm going to pretend I don't know the answer for a few slides, and then I'm going to answer them, and I think that'll be really suspenseful. So the first question we have to ask seems really basic on the surface. What constitutes winning in a game like Deal or No Deal? And a lot of TV game shows, winning is kind of built into the game. But Deal or No Deal is really unique because technically every player is a winner. So no matter how they play, how poorly or how well, the player is going to walk away with at most $1 million, at the very least a penny, which after taxes is like 1/100 of a cent, but that still counts towards winning the game. So obviously walking away with a penny or even $1 is not really great. You can find a penny on the street and $1 on the street if you're really lucky. So in my book, after watching so many episodes of Deal or No Deal, I think there are two possibilities of ways the player can actually win, and they're ordered by preference. So the best possible scenario is that you walk away with a case that has a good amount of money, right? So you made a few $100,000. That's enough to do whatever you want to do. That's fine. Who cares how the game went or how embarrassed you looked when you open all the cases? It's fine. But if you can't open a case with a good amount and you can't take that home, well, at the very least, beating the banker should count as winning. And I think this concept of beating the banker makes sense on the surface, right? The banker makes an offer, you say no deal, your case has more than the banker's amount, you quote unquote beat the banker. But this first point of actually winning a good amount might require a little bit of questioning. What actually constitutes a good winning? So when you look at the board, you might notice, if you actually look very closely, there are two columns. And the game, based on how the audience oohs and ahs and the lights and how Howie Mandel reacts after you open every case, it will make you think that there are kind of two sides of winnings. So this left side here of the lower amounts, those are considered bad winnings. And so if you take home any side or any case on this left side, you've lost the game. But if you take home any case on the right side where the numbers are a lot bigger, then you've won the game and everyone cheers and celebrates. But if we really think about this, you can see $1,000 is really nothing compared to $1 million or $100,000 or maybe even like $50,000. That's not really winning the game. So we have to really ask, what is a good case value? And to do that, we need to bust out the only statistical formula. In fact, this is the only formula I'm going to use in this entire talk. So bear with me here. It's the expected value. In plain English, the expected value takes every single case on that board and multiplies it with the probability that we can actually get that value, and we sum that up for all 26 cases. So you can think about the expected value of 1 million people playing Deal or No Deal, and on average, the 1 million people are going to win the expected value. So what is the board really worth? But in order to calculate that, we need to ask a question within a question, which is what's the probability of actually selecting the $1 million case? So at this final round, you have your case, and there's only one other case on the stage. That means there are 2 cases in total. And you say no deal, and you might think, if there's one case that's unknown and it has $1 million and the other one has $1, what's your probability of having the $1 million case? So you might initially gut reaction say 50-50 chance. I think that makes sense. It's all completely random apparently, but there's one little twist in this that I think will raise a lot of concerns if you're a statistician or you've ever talked to a statistician about game shows. And it's the fact that you can switch your cases sometimes. So you can say, oh, I want to switch my case for the one on stage. I feel like that one has the $1 million. And that really innocent move brings in a whole other problem, which you might have heard of, the Monty Hall problem from the game show, Let's Make a Deal. And so we need to talk about another game show first. I promise this complicated explanation will eventually pan out to the simplest answer, but it's more fun to talk about statistics. All right, so the Monty Hall problem works like this. It's even simpler than Deal or No Deal, believe it or not. There are 3 doors. Behind one of the doors is a really fancy prize, and behind the other 2 are prizes that no one really wants. In this case, 2 goats. And Monty Hall says, pick a door that you think the car's behind. you might pick door number 1, and then Monty Hall opens the door with a goat that Monty Hall knows to be wrong. So in this case, that's door number 3. And then he asks the player the very famous question, do you want to switch your door to door number 2? And the question statisticians pose is it actually advantageous to switch your choice to door number 2? And so just like Deal or No Deal, if you think there's a 50-50 chance the car can be behind door number 1 or door number 2, it doesn't matter. But this is where statisticians will say, everything you've ever learned is a lie. Numbers are a lie. You're wrong, which is just crazy. So here's kind of how this problem actually works. At first, the car can be behind any of the doors with equal probability. There are 3 doors, so 1 out of 3 chance that you're going to get the car. If we add the probability that the car can be behind door 2 or 3, that ends up with a 2/3 probability, which I think so far might make sense. The problem is when Monty Hall opens the door showing the goat, that 2/3 probability still remains. But the probability the car is behind door 3 is now 0 because we know it can't be anything other than a goat. So that 2/3 that was initially for doors 2 and 3 squishes over to just door 2. And this means that the probability of winning the car actually doubles if you switch your door to door number 2, which is crazy. And it blows a lot of people's minds thinking about that. And if you've ever seen an episode of Brooklyn Nine-Nine where they talk about it, it's hysterical. So the difference between the Monty Hall problem and Deal or No Deal is that Monty Hall actually knows where the car is. And so when Monty Hall opens a door, that is really a calculated decision. And that's what causes the probabilities to switch. But in Deal or No Deal, that's actually not the case because every episode of Deal or No Deal starts with this really fun phrase that a third party will always shuffle all the cases, and that the producers and the banker and the audience and the player and certainly the very charming Howie Mandel doesn't know where any of the cases actually are. And so this means after that 3-minute explanation, it all doesn't matter because the probability of selecting the $1 million case is just equal. The probability of selecting any case in Deal or No Deal is 1/26 since there's 26 cases. In this case, that's about 3.8% chance of picking any given case. Okay, don't hate me for that. I promise less statistics going forward. So, all right, well, as I show this formula, maybe I'm a little ahead of myself. So now that we know the probability is equal, this expected value formula, which was really gnarly at first, turns into something that's really simple, which is just the average value of all the cases in the board. And so now finally we can answer this question, that a good winning should be higher or at least equal to the expected value of the entire board, which is $131,477.54. Okay, so now when we look at this, this initial paradigm of the left is bad and the right is good, now we know the expected value is way higher than $1,000 or $5,000 or $10,000. In fact, it turns out that the probability of actually winning Deal or No Deal is less than 25%. The odds are certainly not in your favor of getting a case that's actually worth more than or equal to the expected value of the board. But personally, I would take $100,000 any day. So I don't think that's too bad, but statistics dictates it is. Okay, so we finally established what a good case is. We've established that all cases have an equal probability of being selected. There have been several hundred games of Deal or No Deal. And so my question to you is how many people in the standard Deal or No Deal games that have aired have actually won the $1 million? Okay, take your votes now. Okay, the answer is 0, which is kind of shocking. And when I first found this out, I asked why? How can this possibly happen? And the answer is that Howie Mandel and the player's family who they bring on stage and they ask after every decision if they like that or not. The audience, the banker, all of these factors contribute towards a ton of pressure to the player. And just like in Vegas, where the house always wins, it's the same sort of deal in Deal or No Deal. The more that you play, the more likely you are to lose, and the producers know that, so they'll purposely target the player and just make their life a living nightmare with every decision they make. Again, it's a really funny show to watch. So I had to think, if we really wanted to master Deal or No Deal, and we wanted to play with some performance that's better than human level, we need something that won't succumb to peer pressure at all. Something that has no family, no loved ones, and no considerations for other people. And so the answer is not who does not have that, but it's more what does not have that. And the answer is machine learning. Yay. I want to use a machine learning algorithm to play this game and play it better than a human would. But in order to do that, machine learning algorithms need a lot of data. So we think about ShopRunner. We can't just show an algorithm 1 or 2 shirts and say, here's what a shirt is. We show it thousands and thousands of shirts before it starts to understand what a shirt looks like. Same sort of deal in Deal or No Deal. I've made that joke twice. I should stop doing that. There's only 300 episodes of Deal or No Deal, and that's not enough for a machine learning algorithm to really understand how the game works. And so sadly, there's only 300, we need more than 300 games. And so instead of me just pretending what the game should be, I thought, why don't we use machine learning to actually recreate how the game Deal or No Deal actually plays? All right, so we've talked a lot about how Deal or No Deal works. I think it's a pretty simple game. And anybody with basic Python knowledge might be able to really quickly code up how the main logic of the game works. And I know that's not too impressive. But there's one thing I've kind of skipped over that is actually somewhat important. And it's the banker, specifically what offer the banker makes at the end of each round. So there's a lot of speculation about this online. If you didn't know, like Deal or No Deal Internet is just a wonderful place to be. There are blog posts and Quora answers that tell you that you're wrong, you shouldn't have asked that, which all Quora answers say that. There's blog posts, and there's blog posts, and there's even a PhD student who wrote their entire thesis on what the banker's offer is, which is pretty incredible. But all of these are wrong. And really, to answer this, you can't just watch a few shows. You need to actually have enough sizable data so that we can actually learn how the banker's internal logic works. And so in preparation for this talk, I had to collect data. And data I collected, and in part, I lost a little bit of my soul. So in total, I watched 669 bankers offers, 83 contestants played Deal or No Deal, 62 episodes, which totals up to more than 46 hours of Deal or No Deal. So many Deal or No Deal episodes. I can quote some of them by heart. I am not the same person who went into this talk a month ago. I'm changed. I don't know, it's for the better. But from watching all these shows, I can tell you, and you can trust me because I've watched more Deal or No Deal than anyone in the world except Howie Mandel, that the general banker's formula works with about 2 notes. So the first is that the offer that the banker makes is a function of the expected value of the cases left. And I think this seems pretty intuitive on first glance. If there are really high values of cases that have been unopened, the banker is going to make a really high offer to buy the player's case. And if there are really low values, like just the penny, $1, and $5, and those are the only cases that are left, the banker's offer is going to be somewhere around $3, right? I think this makes sense. Cases left determine what the banker is going to offer. Here's something that might be surprising until 20 seconds from now when I explain it, that the offer the banker makes is actually going to be smaller as the game is beginning, and it'll grow over time as the game continues. And I think this also makes sense when we think about if the banker just made a fair offer to the player on round 1, a lot of players might just say yes, deal from the get-go. And that might mean that each episode they need to churn out about 7 or 8 contestants per show. And each of these people are winning a ton of money. And then the producers go broke. And now there are not 300 episodes to just make our lives better. There's only like 3. So the banker will purposely offer a really low amount to the player towards the initial few rounds to encourage them to keep playing. And then eventually that offer will get more and more fair as the game continues. Okay, so if you wanted some empirical evidence about what I just said, here's this plot. That plots on this x-axis on the bottom, the round number, and on the y-axis going up, it plots how much the banker actually offered. And you can see with this blue solid line that there's definitely this linear positive trend that as the rounds continue, the offer the banker makes tends to go up. But you'll also notice that this blue highlighted area around that line is the margin of error. And that margin of error is really important towards actually predicting what the banker's model was getting. Because all these papers and blog posts and theses, I'm sorry about the thesis, whoever wrote that, I'm sure they don't work at ShopRunner, but I'm still sorry for what I'm about to say. Reporting an error of $8,000 is actually not really that great. Because if round 9, the banker offers $150,000 and your error rate is $5,000, predicting $145,000 is not too far off. But in this lower round, if the banker offers $5 and your model predicts $5,005, that's this huge difference, right? That's not even anywhere close to what the banker actually offered. And so no matter what I did, I couldn't get a model to actually learn without doing some feature engineering. And to do that, I had to introduce one new column of data that magically solved all my issues. And I call it the percentage difference. What this does is it takes the banker's offer and it divides it by the expected value of the board. So how much should we expect to get from all the cases that are left? And if you want some proof, here's that same plot, but on the y-axis is now percentage difference as a function of the round. And you can see that, again, we have this really strong linear positive trend. But more importantly, if you look at the error rate around that blue line, it's steady and pretty constant as the rounds go on, which means if we report a difference of, an error of 0.02, that means that 0.02 will hold no matter if it's a low offer or a high offer, which is brilliant. And now we've cracked the banker's code. So the first thing I did was I trained the linear model and I saw how well it did. There's this error rate on the right column. Don't worry about that. Just believe me when I say lower is better. No more math this talk. So I trained this linear model, but I found there was still a little bit of error. And I realized that the banker probably, like all humans do, try to follow a certain pattern. But eventually you have these little yes/no questions that you ask. So you might say, do we like the player? Okay, then let's bump the offer up a little bit. Have they opened the $1 million case? Yeah, they have. Okay, let's make it a little bit lower. And you ask all these yes/no questions. And so in machine learning, these yes/no questions are represented with another kind of model called a decision tree model, which literally just asks questions. The model says yes or no, and then you follow the tree down until you get to some sort of offer. And so building just a decision tree model, we get an error rate that's a lot lower than the linear model. But it's not perfect yet because I sadly couldn't sleep at night because I had one more question in the back of my mind. And this question would prove to be my doom. Is the banker's formula actually deterministic? So that means if the same game happens multiple times, will the banker's offer be the same for each one of those games? Intuitively, you might say yes, but the answer is sadly no. I found in the data I collected, there were 3 instances where the same game happened and the banker made offers that were up to $15,000 different, which is a pretty sizable amount. Which means the general banker formula follows a trend, but that trend can vary due to randomness or how the game state works. It's kind of all over the place. And so that means that when we look at a model, we need a model that will give a different answer every time we call it with the same data, which is completely the opposite of how we would expect data science to work. Imagine if our taxonomy model said something was a t-shirt only sometimes, and then sometimes it said it was a dress. That would just be awful and we would get fired. But I guess I'm trying to get fired. So how does this work? The banker's offer is actually what I'm gonna call a random ensemble model. What this means is it makes a linear model prediction, it makes a decision tree prediction of what the banker is going to say. And then at any time, it randomly decides who we're gonna listen to more, we sum those up, and that's our final offer. So this seems like a total mess. I'm sure a lot of the data science people here are really mad at me for even making this abomination, but it actually does turn out that the error rate on average is a lot lower for this random ensemble model, which is kind of neat. And this means that we finally have an accurate way to predict the general banker's trend of what's gonna happen based on a game. And that was the final piece. We can finally start playing the game. So to play the game, I had to introduce a new type of machine learning model. This is called the DeepQ learning network. Inside of this DeepQ learning network, it's actually a really tiny neural network. It's so tiny, like compared to our ShopRunner models, it's like a fraction of a fraction of a fraction the size. You can get like all of it tattooed on your hand and have plenty of room to spare. It's really tiny. But the way it works is that it can actually interact with an environment we're gonna call the deal or no deal environment. So unlike the game where you can actually go on stage and you can experience all the ambiance, the deal or no deal environment is very black box. We don't show you what's happening at all on the inside, even though technically on the inside is our banker's model and all the logic of how deal or no deal games work. Our agent doesn't know this. It only knows what the environment tells the agent, and then the environment allows the agent to tell it one of 2 things. So let's kind of go through how this works. So the environment plays a game, it stops, and then it tells our model, hey, here's all the cases that are left, here's the banker's offer, and here's the round number. And then the agent can tell the environment, based on that, deal or no deal. And that's it. This allows the model to actually play the game. The game is shockingly close to the real one. That's how it works. So at first, our model might not know anything. It doesn't know what cases are, or a banker, or even how charming Howie Mandel is. So what happens is, it's round one. The environment says that the banker has made an offer of $8,000, and the agent can kind of just guess. So it guesses deal, which if you've seen Deal or No Deal, you'll know that $8,000 is awful. What we can do, though, unlike a real game, is we can actually fast forward a parallel universe where the model had actually said no deal and continued playing. And we can see that as we fast forward, if the model kept playing, it would have made a maximum banker's offer of $91,000. And so it didn't bring on the good case. It didn't beat the banker. And so, like any good parent would to a child, we need to strictly punish it for performing poorly. Okay, so now it's another game. Our model knows maybe a little bit more. Now it might be round 9. The bankers just made an offer of $163,000. Our model again says deal. We fast forward the game and we realize that technically our model beat the banker. That was the highest offer the banker was ever going to make in the game. But if it said no deal, it would have opened its own case and had $500,000 in there. And so technically it's kind of winning, but kind of losing. And so we punish it a little less strictly. Okay, now the model knows a little bit more, but it's still really nervous. Now it's round 8, the banker makes an offer of $81K. The model says deal, it's kind of waiting to get punished, but we fast forward the game and we realize that its case had less than $81,000. That was the highest banker's offer that was gonna happen all game. It correctly said deal at the right time, and we reward it. It did something really good. And so that's what happens over and over again. Our model just kind of explores how deal or no deal works, and eventually it starts making its own decisions, and eventually it starts to win a whole lot. And so forget 300 games. My agent played 16,000 games of Deal or No Deal. It really understands how Deal or No Deal works now. And now we can actually answer, right, it's learning. So now we can actually answer this question, does a model play better than a human at Deal or No Deal? So the plan is really simple. I'm gonna have the agent play the exact games that the humans did. I'm gonna compare how much the agent won versus how much the human won. And then I'm gonna eventually have my agent go on Deal or No Deal and just make me a millionaire, or at the very least a thousandaire. So here are some baselines, just kind of really simple implementations, which is really sad for humans because a model that's just random, if it says Deal or No Deal randomly, it beats humans about 20% of the time, which is not really great for humans, right? More importantly, the model that only says no deal and just makes it to the end of the game every time beats humans about 40% of the time, which is really sad. Why are we like this as humans? So my DeepQ network beats humans a little bit more than the majority of the time, about 54% of the time. My DeepQ network that's played 16,000 games makes decisions on these actual games better than humans. But I'll undercut myself a little bit by saying that a model that only says deal if the banker makes an offer above the expected value does almost just as well, which is not super great. It means my DeepQ network is more human than I wanted. But I know I have a little bit of time, but I have to tell you, I had this secret backup plan in the back of my mind the entire time because I knew I would fail. I didn't trust myself the entire time. My DeepQ network, it wasn't machine learning enough. And so what I did was I also made a second thing called a look ahead bot. It looks just like the DeepQ network, but it has binoculars. The way it works is that it can take a current game state, it can take that all in, and it can compute 100 games of the future, and then calculate how many of those games ended in a winning, and then it can return that as a probability that we should continue or accept the offer. A really hacky, superhuman way to play the game. But believe it or not, it ends up beating humans about 70% of the time. This is the way to do it. Parallel universes for the win. And so with that, I'm gonna be really rich. I'm playing Deal or No Deal. I'm gonna win the lottery. I'm gonna win $1 million. So that's it, that's my talk. All my code's available on GitHub, it's open source. Even the models are there. It's a really fun README. I like to thank my partner, Jenna Blasey. She's here, she's my live studio audience. She watched a lot of Deal or No Deal for me, and she didn't complain when I talked about it entirely for the last month. Here's my conclusions. You can see this later. Thank you.
Cool, thanks, Nate.